This video will go through question 1. The very first question, we have a decay that we need to write for uranium-238, and in the question it says that a helium is produced and the uranium decays into thorium. Okay, so we need to include this into the decay equation. So I'll write TH for thorium plus the HE 4 and 2 for helium. So just looking at the numbers here, we know that the total mass needs to add up to 238. We have 4 here, so that means this is 234. Okay, and then the proton number, we have 2 here, so this must be 90. So that's it for the 2 marks. The second question, if you read it carefully, it says that the helium can be produced when this tritium decays. So the decay starts with tritium and it decays into helium. Now, for that to happen, you can see the proton number went up by 1, but the mass number stayed the same. This is a sign that it's a neutron turning into a proton, which is just beta decay. Okay. There's also a neutrino produced, but for this question it's not really required for you to write this decay, but it does help you see what exchange particle must be responsible for a decay. Now normally with all decays, a decay is another sign that this is a weak interaction. But the major sign is that we have leptons. Leptons are made, and only the weak nuclear force can do that. So it's a weak interaction, and we know that a beta minus particle is produced, so the charge has been of -1 has been made in this weak interaction. Therefore the exchange particle that must have been involved is the W minus particle. Okay, so to add on to this answer, we have an explanation that a neutron turns into a proton. So it's a beta decay. Okay. Next question, we have a diagram here showing the spectra of helium, sodium and hydrogen. Now the question is asking you to discuss, and in the context of this question we have to make a comparison between the helium spectra with sodium and hydrogen, and we're trying to find evidence for and against the suggestion, which was that scientists suggested that the lines of helium can be seen in the absorption spectrum of the sodium and hydrogen. So really it's just about looking at these lines and seeing where they might appear in sodium or hydrogen. Now you could see that there is a line here. Line C seems to match with hydrogen. So the first point is to say that line C in helium is seen in hydrogen. Okay, so this is a argument 4. Line E is seen in sodium. So line E in helium is seen in sodium. So this is also evidence 4. But there is a line that isn't in either one, and that's line D. So line D here doesn't appear in either sodium or hydrogen. So line D in helium does not appear in sodium or hydrogen. Okay, now the other lines, the reason why we might have ignored A, B and F is because they don't really match up with anything, and also they are quite close to the line, so we're looking for clear lines that are exactly the same and clear lines that are not the same. Okay, second to last question here. This is a calculation, and they want us to calculate in EV, so we have to make sure we keep in mind we understand this unit, electron volt, and how to convert that from joules. This is a unit of energy. And we want to know the change in energy responsible for the spectral line labeled E. So if you go back to figure 1 and look at E, E seems to be I mean, you can estimate this to be, I'm going to estimate to be around 590 nanometers. So line E is due to photon of wavelength 590 nanometers, which means I can use my energy of a photon equation, hc over lambda, to get the energy of the photon in joules. So when we do that, you can use your formula sheet to find hc values, divide it by 590 times 10 to the minus 9, making sure I've converted nanometers into meters, and you get an answer of roughly 3.37 times 10 to the minus 19. And this is in joules. So we want the answer in electron volts, so you should know the conversion. So convert to EV means we take that energy and divide it by the charge of an electron, 1.6 times 10 to the minus 19, and you get 2.11 EV. The final question, I thought it might be useful to look at this diagram to help us understand the difference between an emission spectrum and an absorption spectrum. So in this diagram, just get my laser pointer here, you can see we have a continuous spectrum here, and the way that this is produced, it just helps understanding this, is that you might have a white light source going through a diffraction grating, let's say, and we see all the colors of the spectrum, so there's no lines missing and all the lines are visible, and it's a continuous spectrum. So the way an emission spectrum is produced, or sometimes called a line spectrum, you can see these individual lines of color that refer to specific wavelengths, and that would be emitted by a gas that is excited, and then when it de-excites, it emits a photon of light, goes through the grating, and then we see the spectrum. So each gas, each element will have a unique set of lines like this, and they are taken from the transitions that the atom takes as it gets de-excited and emits a photon, and there could be multiple transitions, and each line corresponds to one of the transitions. In an absorption spectrum, we have same thing. We have white light this time, which goes through, say, a gas. A gas is in the way. Now this gas also, just like any other element in gas, will have a set of energy levels, and if a photon of light is absorbed and that energy of that photon is equal to the energy gap, the photon is completely absorbed. And if it's absorbed, it doesn't get through, and therefore this appears as missing lines in an absorption spectrum. So these gaps where you see the black lines are the photons that have been absorbed. So this question is really asking you to describe the difference between these two types of spectrum, the emission spectrum and the absorption spectrum. And it says with reference to the processes within the atoms, so we have to say specifically what's happening to the atoms to produce this. So in an absorption spectrum, we have the atom will absorb photons and become excited. And these absorbed photons are seen as the missing lines. The missing lines in the absorption spectrum. In an emission spectrum, we have excited atoms de-excite and emit a photon of a specific wavelength. And these are seen as lines in the emission spectrum. Okay, so that concludes question 1. This video will go through question 2. So the very first question is asking to describe the quark character in beta minus decay, so the change in the quark character. So we have to recall that in beta decay, a neutron turns into a proton, and you need to recall the quark structure of each one. So a neutron is up, down, down, and a proton is up, up, down. So you can see that the change that took place is a down quark becomes an up quark. In the second question, for 2 marks, we have to explain how this result, this graph, supports the existence of an antineutrino. So the first point to make is just describing what you see in this graph. You can see that there is a range of kinetic energies for the beta minus particle. Now the thing is, all beta decay is the same. In the beta decay we know that a neutron turns into a proton, as we described in the first question. So regardless of what nucleus is undergoing beta decay, it's always the same process. A neutron turns to a proton, releases a beta minus particle. So they were expecting all the beta particles to have a fixed amount of energy, a maximum amount. So to account for this missing energy, they predicted the existence of a neutrino. So we need to say all beta minus decay expected to have the same energy. So missing energy must be carried away by an unknown particle, which they called a neutrino. Okay, it was called a neutrino because it was not charged. They knew it was a charged particle, and it was very, very small, and that comes from the Italian to be neutral and very small. In this question, we have to identify this missing particle, and with any of these interactions, it's always a good step to write down your properties of each particle, thinking about its charge, the lepton number, and the baryon number. So you just assign values using your data sheet. You can find values for these. So a neutrino is not charged, a proton has a +1 charge, electron has this positron has a +1 charge, and therefore, thinking about the conservation of charge, this missing particle has to have 0 charge. Lepton numbers, again, look at the data sheet. You see this is lepton number of -1. Proton is not a lepton, so it has a lepton number of 0. This is also -1. Lepton number is already conserved, so that means X is not a lepton, has a lepton number of 0. We'll check baryon numbers. Again, data sheet, this baryon number of 0, baryon number of +1, baryon number of 0. So to conserve baryon number, we know that X has baryon number of +1. So without knowing what X is, we already know its properties. It has no charge, it's not a lepton, it's a baryon. So it must be a neutron. In this final question, for question 2, we have to do a calculation understanding the process of annihilation, and it's specifically positron annihilation. So if you remember, with matter and antimatter, annihilation takes place when matter interacts with its antimatter counterpart, and antimatter has the exact same properties except in terms of mass, but not the same charge, the opposite charge. So if I were to draw a diagram of this interaction, we can say we have a positron and an electron, and when they interact, the process of annihilation converts the entire mass of the rest energy and total kinetic energy of this particle. The entire mass is converted into 2 gamma photons. So we have a gamma photon here and a gamma photon there. Now we have to figure out which one of these photons is possible, photon energies are possible here. So what we need to understand is that these electron and positron, these 2 particles, they have a total energy that is made up of the rest energy plus any kinetic energy. Now if we are trying to find the minimum energy needed to produce these 2 gamma photons, we're going to take this to be 0 and just use the rest energies. Now rest energies are found on the data sheet, and you can find the rest energy of a positron or electron is equal to 0.51 mega electron volts. So in annihilation, if a positron and electron meet, total energy in that annihilation process is equal to 2 times that 0.51, which is equal to 1.02 mega electron volts. And if we're saying that this energy is being converted to produce 2 gamma photons, each photon has 0.51 MeV, so just half that number again, it's just back to 0.51 MeV of energy. So on the table we have the photon energy in joules, so we should convert this into joules. So converting into this joules is times 1.6 times 10 to the minus 19, and then times 10 to the power of 6 to deal with the mega. So this in joules becomes 8.2 times 10 to the minus 14 joules. So remember, this was the minimum energy of a single gamma photon here. Okay, so that's the minimum energy. And if you look at the table, neither G1 or G2 photon has that minimum energy. But G3 has an energy above this number, so therefore G3 is the only possible photon energy. So it's G3. This video will go through question 3. So the very first question relates to this diagram of a door and a hinge, and we've been given some data down here of the diameter, length and weight of this cylinder A. We've also given a table of different densities of materials. The very first question is asking us to figure out or deduce which one of the 3 materials is used for A. So if we use the data in A, this data here, we should be able to work out the density of that material. So density is equal to mass divided by volume, and we could get the mass from the weight. So the weight was 35 newtons, so the mass is 35 divided by 9.8, and we get 3.6 kilograms. The volume is found by doing the cross-sectional area times the length, and that is given, length is given as 0.23, but to get the cross-sectional area from the diameter we have to use the equation for an area of a circle. You can use pi r squared, or if you want to use diameter directly, it's pi d squared over 4. Okay. When you do that, you get a volume of 4.2 times 10 to the minus 4 meter cubed. So then finally, density being mass divided by volume, put this mass in, put this volume in, and you get a density of, the 2 significant figures, 8,600 kilograms per meter cubed. And looking at our table, it has to be brass. The next question here, we have to figure out the force, the tension at C. Now it looks a bit complicated, the drawing, but you can simplify this with a free body force diagram. First of all, understanding some of these points about the pulley being frictionless, the pulley M has a negligible weight, it just helps the calculation easier. When it comes to frictionless pulleys, it means that the tension, wherever the tension is at a certain rope, that is carried along the entire rope. So the tension here and here is all the same. So in the previous question, we know that the tension in this rope comes from the weight of A, so the tension in this rope is also 35 newtons. So coming back to this, I know that the weight here is 35, sorry, the tension there is 35 and the tension there is 35 newtons. If I draw a free body force diagram, focusing on this pulley M, because that's where all the forces that I'm interested in are acting at M, so here is that point M. There's the force C I'm trying to find. here's the 35 newtons here and the 35 newtons there, and we know the angle between them is 55 degrees. So remember, point M is in equilibrium. It's not moving left or right, which means the total force to the left, C, must be equal to the total force to the right, this force here. Now, obviously, we can't just use 35 plus 35 because it's not pointing to the right, so we need to resolve these forces. We need to get it to point down like that, towards there. And you can use the crush and stretch rule to help you resolve forces quicker. So in this case, 35 crush 55, so that's 35 cos 55. And then I do the same for this one, plus 35 cos 55. So in other words, it's 2 times 35 cos 55. And that should give me my force C. And when you do the calculation, it gives you a value of 40.2 newtons. Okay. For this part, we have to explain why there is an increase in tension to the horizontal cable C when the pulley M is pulled to the left as the gate is opened. Okay. So when you look back at the diagram, you have to just try and imagine what will happen if this gate is pulled forward and what it will do to the tension on these ropes, so the 35 newtons and the 35 newtons here. And as the pulley M moves to the left, it actually decreases the angle in here. Okay, so these forces, these tensions, will no longer be 35 in order to keep point M still in equilibrium. This still has to be in equilibrium. So considering that, if we write, what's happening here, why the tension increases, we have to mention the idea that the point M is in equilibrium, and angle 55 degrees decreases. If we go back to that equation we did over here, okay, we said that the force C has to be equal to 2 times whatever the tension is times cos whatever the angle is. Now, I have to go back a bit actually and say, well, the thing is that this value of the tension, it can't change because it's still attached to this weight A, so we still know that this is 35 newtons and this is 35 newtons. Okay, so explaining what would happen to C as a result of that, looking at our equation, we said that C was equal to 2 times 35 cos theta. Now if you look at the equation, as this decreases, it increases the whole value of C. C increases. Okay. For this question, we have to recall our knowledge of moments and the equation for moments. We could see it's a moment question. You've got the hinge here that acts as a pivot. It's asking you to calculate the moment of the tension about the hinge. So just a reminder, moments is equal to force times a perpendicular distance. Okay, this bit's important, so making sure we have a force vector and a distance vector that are 90 degrees to each other. So if I just draw this a bit more simplified over here, I've got my door. There is a force here for C. The pivot is there, and the distance here is 0.95 meters. Now at the moment, if you look, this distance and this force is not 90 degrees, it's 12 degrees. So we need to resolve this so it points 90 degrees in this direction. So again, the way to resolve that, look, we're having to move this force in this direction, which is stretching the angle 12. Yeah, and it becomes that this force here is 41 sine 12. Okay, we know that this value is 41 newtons, it says it here. So the component that is perpendicular to that distance is 41 sine 12. So now my force, 41 sine 12, and distance 0.95 are perpendicular. and I could use my moments calculation to do that now to find the answer, which is 41 sine 12 times 0.95, and that gives you a value of 8.1 Newton meter, and that is anti-clockwise, just to make sure we give a direction. It's not really needed, but it's an anti-clockwise moment. For the last question of question 3, we have to discuss changes that would need to be made with the design, seeing that if there are stiffer hinges, when you open it, the weight of the attached cylinder is not enough to close it. So this weight here is not enough to close the gate. So if we go back to this example, if this gate was open and it stays opened and it's not closing, remember, for it to close, it needs to have an anti-clockwise moment. It needs to have a moment to bring it back closed. So in other words, we need to find a way to increase the anti-clockwise moments, which is, remember, the equation force times distance. So to increase m, the anti-clockwise moments, we need to find a way of increasing f or increasing d. So how do we increase the force, right? So first of all, where did the force come from? Where did this 41 newtons come from? It must have come originally from whatever weight of that cylinder was. So you could, as one change, do increase weight of A, which increases tension, or the force, and hence moment. Okay, so that's one thing we do by increasing F. The other thing we do, looking at this equation, well, how can I increase D? How do I make D bigger, the distance between the pivot and that point where the force acts? Well, what if I move the force a bit further along and I had it here? If I had it here, my perpendicular distance will increase, right? So therefore, another change you could do is increase distance between the hinge and force where C acts, which increases the moment again. Finally, I mean, you only need two, but there is another one we could do here. If you look back at our equation, look at what actually increases the value of the moment. We said you could increase the force, you could increase the distance, but notice this number can also be changed, right? So if you know your sine function, as the angle decreases, it increases the value of sine theta. So we need to find a way of making this angle here smaller. So one way you could do that is if you move this pulley R to the right. So if the pulley R was moved more away from the hinge, it will decrease the angle theta. So pulley R moved away from hinge decreases angle and therefore increases moment. In this video we'll go through question 4 of the June 2022 paper 1. So we have a circuit here, and there's a resistor and a bulb, and they've given us two values of this bulb, the power and the voltage across it, for its working potential difference. And we want to work out that the resistance, or show that the resistance is about 9 ohms. So since we've been given the power of the bulb and the voltage across it, we can use P equals V squared divided by R. Rearrange that to get R equals V squared divided by P. So that's 6.2 squared divided by the power of 4.5, and you get 8.54 ohms. Okay, so we want to write it to more than one significant figure, since it's to show that question. In the next one, we need to work out the terminal PD across the battery is, well, we've been told it's 6.2 volts, and we need to calculate the EMF of the battery. So the terminal PD meaning that this is the voltage that is being supplied to the circuit itself, so that's the voltage across this resistor here, and the voltage across the bulb. So one thing we could do is, since whenever we have a circuit and we start labeling things we know at each part of the circuit, we should always work out other things that we can from that information. So for example, in this line, if I know between these 2 points there's 6.2 volts and 12 ohms, I could work out the current in that line. And the current in that line, using V equals IR, or V divided by R here, is 6.2 divided by 12. And I get the current in this line to be 0.517 amps. So I can label that here and say 0.517 amps. I could do the same thing here. And again, between these 2 points, we know it's 6.2 volts, and we worked out in the previous question that it was 8.54 ohms. So again, I can work out the current using V divided by R, 6.2 divided by 8.54, and I get the current in that line to be 0.726 amps. So that's the current here as well, 0.726 amps. So that means, as using Kirchhoff's first law, the current 0.517 and 0.726 join up at this point, and so therefore the current through this cell is the addition of those two currents, so 0.517 plus 0.726, and I get 1.24 amps. Okay, so notice annotating the circuit really helps with then solving the problem. If I want to know what the EMF of the battery is, I can use the internal resistance equation. So if I go to the question now, in the formula sheet we have this as the internal resistance equation, and just reminding ourselves that the current here is the current through the cell, lowercase r is the internal resistance which we've been given, and r is the total terminal resistance. So to work out r, since we have two resistors essentially in parallel, we have to use the addition of resistors in parallel rule. So the 1 over R1 plus 1 over R2 is equal to 1 over the total resistance. So doing that, that's 1 over 8.54 plus 1 over the resistance of this resistor, which is 12 ohms. Okay, and then remember to do 1 over the answer when you get this. The final answer for the total resistance should be 5 ohms. So we now know that this is 5 ohms. Going back to the question, the internal resistance of the cell is 2.5 ohms, so this is 2.5. And we just worked out the current of this through the cell to be 1.24 amps. So putting these values into the equation, you should get an EMF like this, so 2.5 plus 5 times 1.24, and it's about 9.3 volts. Here we have to work out the resistivity of this wire, and we've been given some information about the wire, such as its diameter. Okay, so the diameter is 0.19 times 10 to the minus 3 meters. We've been given its resistance as 9 ohms, and we've been given its length of 5 meters. So the resistivity equation from the formula sheet, we have resistivity is Ra divided by L, and we just need to work out the cross-section area first. So area of a circle, pi diameter squared divided by 4, and when you put this number for the diameter into this equation, you get an area of 2.84 times 10 to the minus 8 meters squared. So putting this into the equation, so the 9 times this cross-section area we just worked out, divided by 5, and you get a resistivity of 5.1 times 10 to the minus 8 ohm meters. With this question, we have to explain with that calculation what happens to the brightness of the lamp as the contact is moved. So when you look at this variable resistor, it's just made up of a wire wrapped around a tube, and as you move the contact, what you're essentially doing is increasing the length of that wire. So for example, as it is now, the length of the wire used is from here to here, and that will give a resistance for that wire. So if the contact is moved to the right, you are increasing the length of that wire in the circuit. So increase in length of wire, and therefore we know from our resistivity equation, or just general knowledge around resistance in the wire, the longer the wire, the more resistance it has. So therefore resistance increases. Okay, so let's see what would happen if the resistance of that component increases in our circuit. So if you look at this circuit, we're talking about this component here. R increases, and if you notice, if the resistance of this component increases, it just means the resistance of this entire line increases. Okay, so therefore, if the resistance of this entire line increases, the current here must decrease. Okay, so the current in this line has gone down. So current through lamp decreases. Okay, so if the current through the lamp decreases, okay, knowing that brightness is related to P equals IV, so if the current decreases, then the power will decrease, and therefore brightness decreases. Okay. Now the final question. Might be useful to draw this change, and it says the student now connects the variable resistor in parallel with the lamp. So if we go back to the circuit, instead of having this variable resistor in series, it's now in parallel. So you might have something that looks a bit like this. So here's the original circuit with the bulb, but this time the variable resistor is connected in parallel with the lamp. Now this obviously changes a few things. First of all, wherever the terminal PD is the same for all of these circuits, because they're separate loops, and the terminal PD is the same in each parallel loop, so that each component gets the same voltage. So keeping that in mind. So if we do increase, so as resistance of variable resistor increases, the overall resistance of the circuit must increase. Okay. Now to point out as the change from before, last time we said when the resistance here increases, since it's in series with the bulb, it will affect that bulb in terms of its current. But since in this circuit it's not in series with the bulb, the only thing you're really changing by increasing the resistance of the circuit is allowing a larger share of that larger share of the voltage to be in the terminal PD rather than the internal resistance. So the next point will have to be to do with the idea that the amount of terminal PD is proportional to the overall resistance of the circuit, of the terminal circuit, so these components. Therefore, more voltage across the terminal circuit. And since we know again brightness is related to power, I'm going to use this version of the equation now because the voltage has increased for each of these components, and the resistance of the bulb doesn't change, so therefore since the voltage of the bulb has increased, brightness of lamp increases. This video will go through question 5 on the June 2022 paper 1. So we have a simple harmonic motion example of a block on a turntable. First question is asking us to calculate the time for the turntable to complete one revolution. So we've been given the angular speed. In your formula sheet, we have omega, which is the angular speed, is equal to 2 pi over t, and we're asked to calculate the time taken for one complete revolution, which is just the time period. Okay, so rearranging this equation, t equals 2 pi over omega, 2 pi over 1.8, and you get 3.5 seconds. This question, we are asked to draw an arrow to show the direction of the resultant force. Now, for anything moving in a circle, the resultant force is a centripetal force, and the direction of the centripetal force is always towards the center on the circular path that's taken. Okay, so for example, in this block, the circular path it's taken goes around like this. So this is the path taken by the block, and therefore the force points towards the center of that circle. So that's the force. The next one, we've been given the mass of the block, and we need to work out the size of the resultant force, which is the centripetal force. So in the formula sheet, we can use mv squared over r, or I'll use m omega squared r because we were given the angular speed in the previous question. So that's 0.12 times 1.8 squared times the radius, which they told us in the previous part of the diagram is 0.25 meters. So when you do that, you get a centripetal force of 0.0997. In this question, and often when we're asked to reference the laws of motion, Newton's laws of motion, it's not enough just to state the law. We have to put it into context with the question. And in this case, the wording of this question is more about the evidence that there is a net force. So bringing in Newton's laws, for example, starting with Newton's first law, we need to, first of all, remember that the law tells us that if the net force on an object is 0, then it has constant velocity. There is constant velocity. But in this example, there is circular motion happening. So, but in circular motion, direction always changing, and if direction is always changing, remember velocity is a vector. If you change the direction, you change the velocity. So velocity is changing, and therefore that first law doesn't apply. I should also state that this is from Newton's first law. Okay, so you could go with that route, or if you wanted to, you could talk about Newton's second law. Now, I won't write it here because it's either one or the other that you can mention, but in Newton's second law, we know that if there is a net force on an object, so in other words, there's a non-zero net force, resultant force on an object, so the second law tells us that there is a rate of change of momentum, or you could say that there is an acceleration. Now, the definition of acceleration is that there needs to be a change in velocity divided by time. So, for something to accelerate, there needs to be a change in velocity. And we just said in this question that there is a change in velocity because there's a change in direction. So, therefore, there is a net force, according to Newton's second law. This question here, we need to find the length of the pendulum, and they tell us in the question that the turntable of the block completes one rotation in 2.5 seconds, so that's the time period, and the pendulum is in phase with this block, so it must have the same time period. In the formula sheet, we have the time period equation as 2 pi root L over G, and since it has the same time period, we just need to rearrange this for L. So as I rearrange it, t squared over 4 pi squared equals L over G, and therefore L is t squared over 4 pi squared times G. and we put in the time of 2.5 seconds, 4 pi squared times 9.81, and you get a length of 1.55 meters. So this final question, first thing to understand is what it's actually asking. So when it says about amplitude relationship or phase relationship, it means we need to compare one with the other. So it's not enough just to state what would happen to, say, the pendulum or the block. You have to compare the two. And in this case, we know that the air resistance will affect the motion of the pendulum, but the block will remain in constant circular motion on that turntable, going around the circle. So we should hopefully recall that if there is air resistance, if there is any frictional forces, then the amplitude should decrease for the pendulum. So the pendulum amplitude decreases and becomes less than the block. Okay, because the block won't change its amplitude, it maintains a constant amplitude since it's on the turntable. Now, you should be able to remember from our understanding of time period of objects in simple harmonic motion, whether it's a pendulum, mass spring system. In this case of the pendulum, we know that time period of pendulum is governed by this equation. Okay, and notice in this equation all it really depends on is the length of the pendulum, which doesn't change, and g, which doesn't change. So even if amplitude does decrease, time period is independent of amplitude. So even though it is decreasing its amplitude, its time period doesn't change. So it remains constant. And then for the comparison, it stays in phase with the block. In this video we'll go through question 6 into June 2022, paper 1. So we have a diagram with refractive indices for different materials A and B. They're shown in the diagram, and we have one of the angles given, but it's not shown anywhere where it's useful, where this normal line is. But anyway, looking at the question, we need to first explain how the path of ray shows that the refractive index of A is greater than the refractive index of B. Well, we can have a look and see what the angles are when they enter that boundary and when it leaves at that boundary. So, for example, we can see this angle here, we'll call this theta 1, is the angle that it enters, and this angle here is theta 2. Okay, so remember, angles are always drawn between the normal line and the ray line. Now you can see theta 2 is greater than theta 1. According to Snell's law, and from the formula sheet, n1 sine theta 1 equals n2 sine theta 2. We use the same numberings as what's given in the labels as well. So this will be n1, and this will be n2. So if I look at a ratio of the refractive indices compared to the angles, I can see if I rearrange this, I get n2 over n1 is equal to sine theta 1 over sine theta 2. So looking at this equation, first of all, we can see that theta 2 is greater than theta 1. So in this equation, theta 2 is in the denominator, so that number is bigger compared to the number above. Okay, so therefore n1 must be bigger compared to n2. So therefore n1 is greater than n2. And I think if we're going to use these numbers, we should also say in the answer that 1 refers to material A and 2 refers to material B. For this question, we need to show that the angle of refraction for the ray at B is about 60 degrees. Now, first of all, when we finally solve this, we must give our answer to more than one significant figure. Any question where you need to show that or it's about, you always do one more significant figure than what's given. But let's go back to our diagram and figure out, well, what do we know in terms of this boundary. We know the refractive indices, and to use Snell's law we just need to know one more thing, which is maybe an angle here. Now you can see there's a parallel line here, and there's a parallel line here, and we have 43 degrees there, which means using the corresponding angle rule this must be 43 degrees here as well. Now to find theta 1, you can see this is 90 degrees overall, so therefore 90 minus 43 must be my angle of incidence. So theta 1 is equal to 90 minus 43, and we get 47 degrees for theta 1. So writing down the equation again, let's put in our values that we know. So N1 is the refractive index of material A, so 1.62. Sine theta 1, which we just worked out to be 47 degrees, is equal to N2, which is refractive index B, 1.35, sine theta 2. So rearranging this, we should be able to get the angle theta, so inverse sine of all of this, and we should be able to get the angle theta. So that gives us a value of 61.4 degrees, so I'll just say 61 degrees to two significant figures. The final question, we need to draw on figure 12 the path the ray makes immediately after it reaches P. So going back, we're interested in this boundary right here. Now to figure out what would happen, first of all notice the outside refractive index is just 1 because it's air, and the inside is 1.35. So there is a possibility that we may have some refraction or may have total internal reflection. So to determine whether there will be total internal reflection, we need to recall the rule that for total internal reflection to occur, the angle of incidence, this theta that I've written here now, must be greater than the critical angle for that boundary. So in your formula sheet, you can look up the equation for the critical angle, and it's written as sine theta c is equal to n2 over n1, where n1 must be greater than n2. So in other words, that must be the boundary that we're in, and n2 must be air. So using this equation, inverse sine of air, which is 1.0, divided by 1.35. And when you do that, you get a critical angle of 48 degrees. So this is the critical angle. Now we need to determine really whether this angle here is going to be bigger than or smaller than the critical angle. So it just requires a bit of geometry here to figure out the missing angles. If I now start labeling things that I know, so for example the angle in here we worked out in the previous question to be 61 degrees, okay, which means this angle in here must be 29 degrees, 90 minus 61, okay, because this is a right angle. The angle here, remember, in a whole straight line it's 180 degrees, so this angle here must be 137 degrees. So all of that allows us to then work out the angle in here, because again it's a triangle, should add up to 180, and the angle in here is 14 degrees. And finally this theta, since this is 90 degrees in here, 90 minus 14 gives me an angle of 76 degrees. So angle of incidence equals 76 degrees. 76 degrees is greater than 48 degrees, so TIR must occur, total internal reflection. So then finally I go back to my diagram, because it does say to draw on figure 12 to get this mark. You just have to be careful, the examiner will just look by eye that you've done a correct angle of reflection here, where this has to also be 76 degrees. This video will go through questions 7 to 19 on the multiple choice section of the June 2022 paper 1. So this very first question, looking at two quantities that has the base units kilograms meters squared per second squared. So looking at these options here, we can write down some of the units that we do know for each of these. So all energies, I can use an equation for energy such as work done, tells us the unit for energy is Newton meters. Momentum, we can use an equation for momentum being Newton seconds. Moments, equation for moments is force times distance, so that will also be Newton meters. So straight away we see these two, energy and a moment, have the same units, and these can also be broken down into the base units of kilograms meter squared per second squared by using an equation for force such as F equals ma. Question 8 is asking us to give us the order of prefixes from descending order of magnitude, so going from largest to smallest. So looking at these options, we see that this one is not correct because pico is smaller than the milli. Neither is this, because giga is bigger than mega. This one's not correct because nano is smaller than micro, which leaves this as the only option that's correct. I forgot to select this one here, so C for question 7 and D for question 8. In this question we want to work out an estimate of the kinetic energy of a car on a motorway. So you have to think of appropriate values to use to estimate these quantities. So writing the equation down, half mv squared. If we think about typical mass and the speed of a car on a motorway, we could say something like around 3,000 kilograms for the mass. And you could convert motorway speeds, let's just say this 100 kilometers an hour, into meters per second by just turning the units back into meters per second. So that will be times 10 to the 3 and then divided by 60 times 60, and you get roughly 30 meters per second. Okay, so we put that into the equation, square it, and you get roughly something in the order of magnitude of 10 to the 6. So this is the correct answer here. Next one, specific charge. So we recall that the equation for specific charge is charge divided by mass. And charge is measured in coulombs, mass in kilograms. So we need to know the charge of this nucleus in coulombs and its mass in kilograms. So using the data sheet, we could figure out some of these values that we need to use for the charge of, say, 1 proton and the mass of 1 nucleon. So this carbon 6 has 6 protons and then 13 nucleons. We can use the charge of 1 proton to be 1.6 times 10 to the minus 19, and the mass of 1 nucleon. On the data sheet we could use the atomic mass unit, 1.661 times 10 to the minus 27. So we put this into the equation, 6 times the charge of 1 divided by 13 times the mass of 1, and that should give you roughly 4.4 times 10 to the 7. So it has to be A. Question 11, we want to recall the range in which the strong nuclear force acts. So just remembering something like this, starting from 0 to 0.5 and then to 3 femtometers and then beyond. So you should be able to recall that between these two first distances it's repulsive. The distance between where it's attractive, and beyond that distance is no effect. So looking at the options here, the only one that would be correct for this one would be C. Question 12, which of these statements are correct? So you could do process of elimination here and get rid of ones that you know that aren't correct. For example, this first one, all strange particles are mesons. Well, yes, some strange particles are mesons, but you can also have baryons that have strangeness and strange particles, so it's not this one. Strangeness can only have values of 0 or minus 1. Well, on the datasheet we see strangeness can also have a +1 value, so this is not correct. Strangeness can only change in strong interactions. Well, we know for strong interactions strangeness is always conserved, so it can't change. So just from process of elimination we know B is correct. But a little bit about why this has to be correct, because reason why strangeness or strange particles are created in pairs is because you can have an interaction where you have some particles that will produce, well, that will have no strangeness on their own, but they might interact and produce a particle with some strangeness. Now, in order to conserve that strangeness, another particle with an anti-strangeness must be produced. So one of the particles might have a strangeness of -1, and therefore you need another particle, a pair of particles with a strangeness of +1 to balance that out. For number 13, again, we could do process of elimination here and figure out which one of these combinations is possible. First of all, this one can't be possible because you can't have just two quarks on their own. It seems like for a meson, you need to have a quark and an anti-quark pair. So this is definitely possible. This is also not possible because we have an anti-quark but then two normal quarks. But baryons only come in either 3 quarks or 3 anti-quarks. And then D, also for the same reason as before, is not correct. The other thing you could check as well is to see if the charge is a whole number or 0. So, for example, you can't have a fractional charge like this one. This one will be 2/3 and then -1/3, which will give you a third charge overall. A particle can't exist with a fractional charge, so that's why D might not be correct, but B is the correct answer here. For 14, just recalling what we know about stopping potential. So stopping potential is the minimum potential required to reduce the kinetic energy of a photoelectron to 0. Okay, so what does that mean, right? So if you remember from the photoelectric effect, this is the equation. We have a photon that comes along, which has an energy hf. It will provide some of its energy, the photon, to an electron to escape the surface. So this is the work function. And the remaining energy is the maximum kinetic energy of that electron. So that's the energy that the electron has to go from one side to the other in, say, a photovoltaic cell. So this is the energy of the electron. Okay. Now, this electron in a circuit, for example, will have this energy and might complete a circuit in a photoemissive surface and to another electrode, for example. And if you want to stop that electron getting to the other side, you need to match that energy to bring it to 0. So in other words, if you provide an electrical force to repel that electron, the energy due to that electrical force we get from the equation. So electrical energy equals QV, where Q is the charge of an electron, and therefore if that voltage is the minimum needed to stop the electron, that's the stopping potential. So we're looking for this quantity EVS that I just described is the energy required to stop those, the kinetic energy of those photoelectrons. So it has to be B. So number 15, just again recalling what we mean by fluorescence and what the coating actually does. So you should be able to remember that the coating will absorb UV photons from inside the tube and then re-emit photons of visible light. Okay, so this is through excitation and de-excitation of those atoms in the coating. So knowing that, reading through the options, the one that will actually match what we just said here is B, absorbs photons of ultraviolet light and emits visible light. So for 16, we are looking at evidence for particle and wave nature of light. Again, you could eliminate experiments you know that are definitely not for wave nature. For example, the photoelectric effect is particle nature for light, and for particle nature it's not anything to do with diffraction because that's a wave property. So you're left with A as the correct answer. Okay, so recalling the de Broglie equation for this question, lambda equals h over mv. So it looks like to get the smallest wavelength, we need the largest mass times velocity or momentum. So looking at these options, we need one with the largest mass and the largest velocity. So first of all, it can't be the electron and then this proton has a higher velocity, so it's therefore going to have the larger momentum, so it has to be D. Okay, so 18, you have to think about properties of a wave here. If they've told us the frequency is 660 Hz, so one thing you can work out straight away is the time period by doing 1 over frequency, and you get 1.5 times 10 to the minus 3 seconds, or 1.5 milliseconds. So the time period of the oscillations of these particles will be 1.5 milliseconds, and that actually matches with C. Okay, and just to talk about why the others might not be correct, so for example in A, the speed of the wave is 330 meters per second, so we're talking about the energy transfer is that speed, not the oscillations themselves. For D, it says it changes directions 660 times a second. So it sounds like it was trying to describe frequency here. So frequency is the number of oscillations per second. Okay, and in that case, it is 660 Hertz, but changes directions 660 times a second. Well, we know in an oscillation, it will change direction when it gets to the top, and then change direction again when it gets to the bottom. So it's actually 2 changes in directions per oscillation. So the actual number of changes is twice the frequency. Okay, so it can't be D. In this video, we'll go through the multiple choice questions 19 to 31 in the June 2022 paper 1. So this first question is asking about the first harmonic of a standing wave, and we know the equation that gives us the first harmonic on any standing wave is F equals 1 over 2 pi root T over mu, where T is the tension, mu is the mass per unit length, and F is that first harmonic. And they've told us for a particular string where the first harmonic is at frequency F, it has a tension T, and the tension is increased to 40. So if we look at the relationship, we can see F is proportional to the square root of T. So 40 means that this is being multiplied by 4, but because of the square root sign, we're saying F is multiplied by root 4, which is the same as F times 2. So that just tells us in this new tension on this length of string, which hasn't changed its mass or length, the fundamental frequency is now 2F. So F fundamental, F naught, is equal to 2F. So this is the frequency in which you get the first harmonic. So when they say which harmonic had the frequency 2F, it is the first harmonic. Question 20 is asking us about the Young's double slit equation, and we need to recall the equation or write the equation from the formula sheet to get that the fringe separation, W, is equal to lambda D divided by S, where lambda is the wavelength, D is the distance between the double slit and the screen, and S is the slit separation. So this is just from the formula sheet. So if I'm trying to find slit separation, I need to use the rearranged equation, which is lambda D divided by W. So what I know from this question, the wavelength has been given as 5.2 times 10 to the minus 7. The distance to the screen to slit is 1.5 meters, and it says that 10 fringes, the width of 10 fringes, so we have 10 widths here. W just represents one width, the distance between 2 fringes, so I have to just divide this number by 10. So W is 0.35 times 10 to the minus 2 meters, converting centimeters to meters. Putting these numbers into this equation, and you get S equals 2.23 times 10 to the minus 4. So you're left with D as the correct answer here. Question 21 is asking about the diffraction grating experiment, so therefore I'm going to write the diffraction grating equation down, and lambda equals d sine theta from the formula sheet, where n represents the order of maxima, and if you remember in diffraction gratings, you have a central maxima, and then you have some maximas either side. So I just need to work out how many maximas I have either side, and you know, we label these maximas with a value for n. So this is the n equals 0 maxima, this is the n equals 1, n equals 2, and so on. It's the same on the other side, n equals 1, n equals 2. So what we have here is a calculation that we need to do to work out what the maximum possible order we can get with this wavelength and this slit separation. So I'll make n the subject of the formula, and from looking at this right hand side of the formula, noticing that the maximum, if I want to get n max, the maximum value, the biggest value that sine theta can be is equal to 1. So the equation just becomes n max equals d over lambda. Because this is a useful equation to be able to just recall that this is how we get the maximum order number. Put the numbers into the equation and you get n equals 4.3. So n max, since it can only be an integer, 0, 1, 2, 3, 4 and so on, it's 4. So in other words, in our original drawing we have another 2 here, so there's 4 on this side and 4 on this side. So in total we have 9 maximas. Question 22 is vector's problem with motion, looking at how far in terms of its position this plane would get as it goes across, and it does make a right angle triangle, so that's useful to know. So if we want to work out the distance of this hypotenuse, we need the speed times time, and that's given as 150 meters per second as the speed, and it's after 1 hour, so I have to times it by time in seconds, so 60 times 60. And doing that we get a distance of 540,000 meters, or just 540 kilometers. So this is 540 kilometers. And to work out how far north, I just need to know this distance here. So you could just use a trigonometry rule, SOHCAHTOA, use cos 60 equals x over 540, rearrange, and you should get a distance of 270 kilometers. So it's A. Question 23 will require us to use a Subat equation. The ball is thrown vertically upwards and returns to its original position. So in the first part of its journey, it's thrown up and it gets to a maximum height. So we can work out the distance to that point. If we take this to be our start and end positions, write down what we know in Subat. We're trying to get s, initial speed we don't know, final speed is 0 at the top, a is minus 9.8, and it does say in the question that it takes 2.4 seconds to get back to its original position. So in the second part of this distance is travelled, it comes back down to its original position. So both of them together took 2.4 seconds, but since it's symmetrical I could say that time is 1.2 seconds for each. So if I could work out the distance here, and I do a similar calculation here, so when it's coming back down, we know the values s, u, v, a, t for this one as well. 1.2 seconds, 9.8, v we don't know, u could take it to be 0, and the equation to use to get s will determine the total distances that we need here. So to begin with, if I, for example, in this equation, I want to get s. There is an equation you can use to get s from just v, a, and t, but I want to stick to the formulas you're given in the AQA formula sheet and actually work out u first by doing v equals u plus at and get a velocity, initial velocity from this. So using that equation, I am able to work out an initial velocity, which is 11.8 meters per second. And then I could just use the v squared equals u squared plus 2as equation, rearranged, to get s. And doing that, I'm able to get that distance going up, and then I need to double it to get the distance coming down. So that distance is 7 meters, and therefore since the distance coming down is the same, I'll get the same value of 7 meters. If you wanted to, you could use this equation or this side of the journey to do the calculation, where if we know it's v squared minus u squared over 2a equals s, I could have got 7 meters here as well. Okay, so in total it's 14 meters travelled. Question 24 would require us to look at net forces on two objects. So we do have two objects, so we have to think about a free body force diagram on the objects on their own. And I'm only really interested in the horizontal direction. I know both of these, the car and the trailer, so the truck and the car, will have an acceleration of 2.3 meters per second squared. And so there's this one. Because they're connected, they're joined, they have the same acceleration. And it's asking us to work out the tension in the tow rope. So in terms of forces, for this truck we have that there's an engine force, let's call it E, and then there's the tension this way. Can't really do much with that one because I don't know this engine force, so I'm going to look at the forces acting on the car instead. So the force acting on the car to pull it is the tension. That's what I'm trying to work out. And it says in the question that the total resistive forces on the car is 1100 newtons. So looking at just the car, just the information about the car, I could write a net force equation to say, well, the net force, if I take left to be positive because that's the direction of acceleration, then it's T minus 1100 equals the mass of the car, which has been given to be 1.3 times 10 to the 3 times the acceleration 2.3. Rearrange this to get the tension in the car, and you see it's 4090 newtons. So that's closest to B. Question 25 is about diver, parachutist coming down, falling at constant speed. That's what it says in the question. And therefore, if we had to think about the forces acting on this diver as they're falling, we have to consider that for Newton's third law pair, each force has a third law pair. So let's talk about each of the forces acting on this diver. So the force acting downwards on the diver is the weight, so it's the force on diver due to Earth. And then the other force acting upwards, and I'm going to do it as a separate free body force diagram because I want to just separate out the pairs of forces for Newton's third law. Because there is an upward force, but it's not the same type of force, it's not a third law pair with this gravitational force, and that's the force of air on parachute. Okay, or on the diver, we could just say. So each of these must have a third law pair, and the way you think about third law pairs is that it should have the same wording with the objects swapped. So as I said, for this first one, the downward force is the force on diver due to the Earth, it's just the gravitational force, which means that there must be a third law gravitational force on Earth due to diver. Okay, and just like the same format in finding the third law pair for the force of air on parachute, or let's just say for the diver, just to keep this consistent, then there must be a downward force, according to Newton's third law, of force of diver on air. So you see that there is a format to follow when you're identifying third law pairs. So in this question, we're trying to find the third law pair for the weight. So it's the ones we've done here. Okay, so it can't be the drag force, that's not the same type of force. Can't be tensions, because again, that's not the same type of force, it's not a gravitational force. And it can't be lift from the air, because again, it's not the same type of force, and this time it has to be C in this case, because it's the same type of force, and it's on the different object, the Earth. So we've already identified that in our drawing. In question 26, we have to think about, in the question it's saying calculate the change in momentum, so I write my equation for change in momentum is mv minus u in brackets, where m is the mass of the object, and v is normally final speed and u is initial speed. But just to put this into context, a ball is dropped from rest from a height of 1.8 meter and it hits the ground, and then it rebounds. So the final velocity in this scenario is the rebound velocity, and the initial velocity is the impact velocity. So I need to work out these two velocities, the impact velocity and the rebound velocity, and I can use the Suvat equation to do that. So for example, when it's hitting the ground, for the impact velocity, I know initial speed is 0, the distance is fallen is 1.8 meters, and I know that A is 9.8. So using a Suvat equation to get this final velocity, you should be able to get the final velocity for impact will be 5.94 meters per second. In a similar way, I could work out the rebound velocity. Again, I start here, goes up, reaches a maximum height, so v is 0. U is the thing I'm trying to work out. We were told that S is now rebound height of 1.1 meters, and then acceleration points downwards of minus 9.8. So again, using v squared equals u squared plus 2as to get u, you should be able to get the speed for rebound to be 4.64 meters per second. So now I have my impact velocity and rebound velocity. I can put them into this equation, and you should get delta P equals, well, the mass is 58 grams, so that's 58 times 10 to the minus 3. And then rebound velocity is 4.64 minus impact velocity. Now I've chosen upwards to be positive, so the rebound velocity is pointing upward, but the impact velocity points downwards, so it's a negative 5.94. So you end up just adding the numbers. Do that in the calculator, and you should get a change in momentum of 0.614 d. For question 27, we have to think about the energy stored in a spring. So the equation that governs that is half F times delta L. And in this question, they've told us that initially the mass M is suspended in the spring and it has an energy E. So, you could use this equation to work this out. Understanding that the force on the spring is just the weight. So, in other words, F equals mg. So whatever mass been added, that's the weight. And they said in this this spring is now add an extra 2m. So it went from having a mass of m to a mass of 3m, because 2m plus m is 3m, right? So we've tripled the mass, and if we've tripled the mass, then we've tripled the velocity. So, sorry, not velocity, the force. We've tripled the force. So knowing that, if we've tripled the force, we know in this equation F is times by 3. So that helps us figure out what happens to the F in E equals a half F delta L. So now let's look at delta L, the extension. So Hooke's law tells us that F is equal to K times delta L. So the extension is what we need to work out now based on the masses added. So we already said in the previous part that this has been multiplied by 3, which means it's proportional to extension, which has also been multiplied by 3. So we figured out delta L is multiplied by 3 from this bit, and F is multiplied by 3 in this new scenario. So now if I look at the equation, we can see E is proportional to F delta L. If you times this by 3 and times this by 3, overall this has been times by 9. So it becomes 9 times the initial energy. Question 28 is asking us about the stress on a material, strain, extension. It makes sense that if it's going to be mentioning these quantities, we could write the Young's modulus equation, which is stress divided by strain. We know stress is force over area, and strain is extension over original length. Now, just from knowing that stress is force over area, we could eliminate this answer, because it tells us in this question that the force is now twice the value, even if cross-section area is the same, which it says here, and it's the same material. According to stress equals force over cross-section area, if I change the force, I'm going to change the stress, so it's not the same stress. Let's look at the Young's modulus equation with these quantities now. So y equals F over A divided by strain, which is delta L over L. And if I just try and rearrange this to make delta L the subject, because I want to see what happens to extension, that's equal to FL over A times the Young's modulus. Now they've told us that these two quantities is constant. It's the same for both materials. So delta L is proportional to F times L. And they've told us in the question that F is times 2 and L is also times 2 because it's twice the length and twice the force. So extension becomes times 4. Okay, so it can't be B either because it's saying Q has an extension of 2 times that value. Let's look at the strain equation. Now that we've figured out delta L is times 4 and L is times 2, overall the strain is 4 divided by 2, which is therefore times 2. So the strain of Q is double the strain of P, so this is the only correct answer here. Okay. For question 29, we need to work out the charge, which is Q equals IT, and the charge is given to us as 1.5 times 10 to the minus 3, and the time for 2 minutes converted into seconds is 60 times, well, it's just 60, sorry, so 60. And we get a charge of 0.18 coulombs. So this point has a charge that passes through a total of 0.18 coulombs. But they've asked us how many electrons that is. So remember, one electron has a charge of 1.6 times 10 to the minus 19 coulombs. So if I have 0.18 coulombs, just divided by the charge of an electron, and you get 1.13 times 10 to the 18 electrons. So that matches with A. Question number 30, we are asked about combinations of resistors we can make with 3 10 ohm resistors, and which of these is not possible. So I could just draw out all the different possible combinations I can make with these 3 resistors. So maybe I have 3 in series, that's 30 ohms. I can have the 3 in parallel. Okay, and you can use your parallel addition rule. And when you do that, you get a total resistance of 3.3 ohms. So it can't be this one. I could also maybe combine it like this. So 2 of them in series with the other one in parallel. And again, you know, the 2 here in series will be 20 ohms, and this is 10 ohms. And therefore I can use my parallel circuit rule, and I get 6.7 ohms in this example. So it can't be B. Another combination I could do is possibly have 1 in series to begin with, but then the other 2 in parallel. Okay, so again, this one is 10 ohms. Combination of 2 10 ohm resistors is 5 ohms, so the total is 15 ohms. So therefore, C can't be the answer. So D is the only one that we're left with as the possible answer. So last question here now. We've been given some information about something in SHM of time period 1.4 seconds and amplitude of 12 millimeters. So T is 1.4 seconds, A is 12 times 10 to the minus 3 meters. Oh, in fact, I'm going to leave that in millimeters because if I look at all my answers, they're all in millimeters per second, so I'll leave that in millimeters. So maximum speed, in the formula sheet, you should see that Vmax is equal to omega A, and then omega is just 2 pi over T. So Vmax is 2 pi over T times A. Put these numbers in and you get a velocity of 54 millimeters per second. So it's C.